before it was too young. It makes that in both structure and reaction, more reactions from my point of view. But we'll see.
You'll see.
And he's especially interested in clusters as well. So he will tell you in general about reactions and resonances, but specifically on reactions to a light cluster effect in nuclear physics.
How much time do I have?
So we try to go until 1:30, maybe just in a go. If you feel too tired, you just go out one by one, okay? And if you feel too tired, you just
All right, so as it was introduced, I'm going to talk to you today about reactions. So this is the subject of the lectures that I will present. And of course, subject of reactions is very broad, and there are many different aspects. And what I'll try to do is I'll try to be somewhat pedagogical and go from the very beginning, and then towards the end discuss more detailed things. First of all, let me start with some introduction using PowerPoint here and highlight you ideas. Why do we need reactions and what's the nuclear physics is all about? So this is the map of nuclei, the way we're going to discuss it. So this is basically, we think of nuclei as made out of protons and neutrons. These are our degrees of freedom for this discussion. We will not talk about quarks and maybe more high energy reactions. So we have protons and neutrons, and therefore this is the map, neutron number, proton number. Now, if you look at this map, it's rather large territory. So there are over 600 different nuclei predicted, 3,000 observed. There are various types of nuclei, and you heard about a few of them already today. Now, this chart is interesting because you can tilt it, and each nucleus is a quantum many-body system. So there are many nucleons, and these nucleons can be in different excited states. And this is just an illustration for you. In fact, you already heard about alpha particles, and you see it's quite interesting that it's so much bound. So you look at this map, tilt it, and then you can see the states in here. So now, how do we know about all of those states? And that's where reactions become important, because we can only see these quantum mechanical states if we have a way of probing them. Now, and that is the question, how do we probe them? And this is the subject of reaction physics, because nuclei, in essence, can be probed in two main different ways. One is you kick a nucleus, and then it goes into some kind of quick reaction. So you populate the state, and it quickly decays. And then there are another somewhat separate is a decay process. Of course, it can't be related, but this is a decay process when you have a long-lived state, and the state decays, and you can measure this decay. We will discuss that in more details, but there are various aspects here. In particular, there are electromagnetic decays, for example, which is can be rather long-lived. So this is the question of reaction physics. And overall, at the end, I would highlight that the subject of nuclear physics is quite interesting, and there is a lot of research in that area. So coming back to this map. So if you look at this map, it's a color map. And here is on the scale of lifetimes. So you look at this map and you see a very broad variety of different scales. So some of the nuclei in the line of stability, what we call, they're stable. And then there are a lot of nuclei that are unstable, that live for femtoseconds or less. All right, so let me now go to the board and start with you somewhat more detailed discussion of reaction theory. So first question is, we would like to do a reaction, so we would like to do a scattering process. Now, how do we define things here? So the scattering process, as illustrated there, is the following. So in the simplest aspect, I have a target, I shoot a beam, and then there is some scattering, and then something comes out, and here is my detector standing here, which measures counts. So this is my detector here. Now, what we define or what we can measure is a count rate, and of course we have an initial beam current. So J initial is my beam current. And then in the detector we have a count rate. Because the detector is finite, I will refer to this count rate as d omega. So this is count rate. This d refers to small area that I'm covering. So then we can define a cross-section. In there you have it omega, but in principle it's a d omega if we're talking about a small detector. Then I can define a cross-section d sigma as my count rate d omega over J initial. So this is the definition of my cross-section. Now let's look at the units here, which is important. So J is my current. So it is measured. So J is current. It is measured, generally speaking, in particles per area and per second. So second. Okay, so this is going to be my units for the current. Then this is measured. Let me put it units in here. So the count rate is clearly measured per particles per second. So therefore, if I come here for the cross-section, then I have a ratio of these two, and you see that particles in seconds cancel, so I have area as my unit. Okay, so this is important. Now, the simplest discussion of the cross-section is the question of a classical scattering. So what happens in the classical case? Let's talk about that. So in the classical scattering, what I have is it's a fully deterministic issue. So I have a fully deterministic process that if here, well, I can use this picture. So if this is my target here, and this is my beam, then there is a scattering axis here. So suppose my particle comes at some, what we call an impact parameter. So far away, a particle is offset from the center by the impact parameter b. Then this particle has a fixed classical trajectory, and it is going to scatter at some angle theta. So this angle theta is referred to as a scattering angle. Now what is important about classical mechanics is that it is fully deterministic. This b will give me theta. Right? So what is important that from the impact parameter I will always get theta. All right, so now let us do the count rate. So then how many particles that come with this impact parameter b, and maybe with some slightly different b dB interval, will get scattered into that angle. So assuming a rotational symmetry, the azimuthal symmetry here, I also have an angle phi, so this is d phi here. Right. So the area that will be covered in this small interval here, right, is going to be b times dB times d phi. That's the area that is covered. All right. So, and all particles in this area will go into my detector. So therefore, the number of particles per second that goes into my detector is just J initial multiplied by that, and that gives me d omega. So therefore, I can now find from here my cross-section. So my cross-section is just sigma, or d sigma, according to that, is d omega over j initial, which is b dB d phi. And of course, this presumes that all of these are going into that angle theta. So what I can do, of course, is I can relate this to omega. So if I have my solid angle d omega, and the solid angle d omega is sine theta d theta d phi, then I can take a ratio of these two and determine my differential cross-section, which is a cross-section pair omega. So what I will have here is then b dB over d theta over sine theta, and my azimuthal angle cancels. Okay, so this is my equation for a differential cross-section in the completely classical case. Now, there is one important remark that I should give you immediately here, is that if I increase this interval here with dB, so if I make my a little bit larger dB, now the presumption here that the theta is also increasing a little bit. But in reality, whether it's increasing or decreasing doesn't matter, because my particles, I still count the same particles in the detector. So therefore, you should put a modulus here. Okay, so this is my cross-section, and now is a good time for an example. So in the example, we'll have a hard sphere. So if I have a hard sphere, and of course you can always have two hard spheres colliding, but then you just treat radius as a sum of these two radii, right? So if I have two big balls, then the distance how they can come as the distance, what we call of closest approach, is r1 plus r2. So to simplify, I will just treat my problem as one big sphere of radius r, and then the point particle coming at impact parameter b. So then if this is impact parameter b, then I can have this b in here. And then the scattering angle is determined from a hard sphere. All the physics is in the fact that angle of incident equals to angle of reflection here. So it means my scattering will occur at this angle where, let me call this some phi, this equals to that. All right. And the scattering angle theta is this angle. And so in this particular picture, it almost scatters perpendicularly. All right, so then the mathematics here is this is the same angle, phi. So what I know is that the sine of this angle phi equals to this side over the radius, b over r. So, and that gives me everything because I know that this theta that I need, so I have pi, which is 180 degrees, equals to 2 phi plus theta. So from here I have phi equals pi over 2 minus theta over 2. Okay, so therefore I have a sine of this, and sine pi over 2 is just a cosine. So I have a cosine of theta over 2 equals b over r. And this is my most important equation because this equation tells me exactly how my impact parameter is related to a scattering angle. Okay, so now we can further put it into my equations. So I have d sigma over d omega equals So my impact parameter B is r times cosine of theta over 2. Then here I have a sine theta, which I will write as 2 cosine theta over 2 sine theta over 2 using a double angle theorem. And then I have dB over d theta in absolute value. So this is this one. So I should take the derivative. And the derivative gives me of the cosine minus sine, but it's absolute value. And of course, there is r and a factor of 1/2. So I will have r over 2. And then I have sine theta over 2 again. All right, so now you can see that, in fact, it turns out that everything cancels, and my answer is r squared over 4. All right, so this is a rather interesting and remarkable result, that my cross-section when I scatter from a hard sphere is it's uniform. So it doesn't depend on angle. So it means that my particles go out everywhere with the same probability. Of course, there are some particles that don't scatter at all. So then this is determined by the total cross-section. So the total cross-section sigma, which is just an integral of d sigma over d omega. Now, in this case, it doesn't depend on any angle, so this is just 4 pi is the full solid angle multiplied by r squared over 4. So 4 cancels out, and I get a pi r squared. Okay, so do you know why do I get pi r squared? Because it is a cross-section. It's a disk. So for these particles, it looks like a disk. And this tells me that this disk pretty much stops these particles. And that's natural explanation of the cross-section. Okay, so this is a simple example of scattering from a hard sphere. Now, another important example of scattering would be a Rutherford scattering, which I think I have an answer. It's a somewhat longer derivation. So it's a scattering in the case of a Coulomb potential. So in the case of a Coulomb potential, here I give you some results. So in the case of the Coulomb potential, this is a dependence of scattering angle versus impact parameter. And here are two examples. One is the Coulomb potential, another one is the hard sphere. We have just derived the hard sphere. Now for the Coulomb potential, the derivation is somewhat more involved, but you can again do it. And you will obtain this answer, where A is the distance of the closest approach. So which means that if your particle, if this were a Coulomb particle, you start on the axis, you shoot it straight forward, assuming a repulsive potential, it will approach by a distance of A. Right, so this is the equation. Now it turns out that in classical mechanics, again without going to too many details here, classical mechanics you can always establish the relation between impact parameter and an angle, and the scattering angle, using energy and momentum conservation. So this is fully sufficient, and you can always express scattering angle as some integral. Now, of course, you may not necessarily be able to take the integral analytically, but it is always possible to do that. All right, so then what are additional features of the classical cross-section that we have to address here? So one important feature is that sometimes, and in nuclear physics that is particularly important, you can have two impact parameters that lead you to the same scattering angle. So, which is quite common. So suppose you have a nucleus, a rather large nucleus. Now, nucleus has a charge. So if you scatter, some particles can go here and scatter that way because they are repelled from the charge. Then there is another impact parameter on the other side where you enter the nucleus. And when you enter inside, the inner part of the potential, the nuclear force, is attractive. So therefore, it would bend particles towards inward. So it is possible to have these two trajectories. Let me just use the other color of chalk here. So this is maybe a remote trajectory. And we call this a near side trajectory because it looks nearest to me. And then there is another trajectory, which is here, which starts here and bends in the same way. Right? So your detector will clearly measure both. So this trajectory is called far side trajectory. So, and then you have to start making clear distinction between, first of all, there are two issues here. One is, of course, this angle, as you see, that comes from above. So it's deflected that way. This one is deflected in the negative way. If I draw this trajectory here, it would have gone that way. So if you are thinking of a scattering angle, so you have to start distinguishing scattering angle from a deflection angle. So, and your scattering angle is always between 0 and pi. And you can always think of it as being in the upper side. But you get both contributions from all of them. Okay, so that's one issue. And of course, then there is another issue that you, like here, you have two different trajectories. So you start generalizing the problem, and that means in your scattering cross-section in this equation, d sigma over d omega, you essentially have to sum, so 1 over sine theta can be outside because this is your scattering angle which is outside, but then you have to sum over all possibilities, which I list as I, that give you the same scattering angle. So you sum here of b db over d theta modulus, and this is I for each possibility. So here I would be two possibilities. Okay, so this is a classical discussion. In quantum mechanics, which we'll get back to, these different trajectories, they can interfere with each other. So that makes it a difference. Okay, so then there is another interesting discussion here is what happens if, let's say, d theta over dB, which I wrote it in reverse, equals to 0. So what happens in that case is that your cross-section diverges. Another possibility for divergence is if the sine theta is 0. So, and that is easier to understand. If you have a certain trajectory, so of course if you start with 0 at the axis, presumably if you have enough energy you go through, then you get 0 outside. So that would be the case of sine of the angle being 0. But I'm talking about another situation. Let's say in here there is another trajectory that when you approach, it first bends outward. Then when it goes inside, it's bended inside. And then it comes out again that way. So it comes out straight. So in this case, what you will have is a kind of focusing effect. So you have another trajectory which is added to the central one. So this focusing effect also will lead to an infinite cross-section. Okay, so this is a situation with the classical scattering, and one very good and interesting example of that is rainbow scattering. So if you look at the sky, you see the rainbow, and the question is, why does the rainbow happens? All right, so let us talk why you would see a rainbow. First of all, can rainbow be just a, so if I have a liquid drop in the air and the light scatters out of it, it just basically comes, hits, and reflects. So can then I see a rainbow? What would I see then? Anybody has any idea? Well, the answer is I won't see anything. I see a uniform glow, and this is the blue sky, because as I just showed you, the scattering is uniform, right? So if I have a drop, there's nothing special. It's uniform. So in order to see something, I have to see something, or something else has to happen. And of course, this something else is my light goes in. Somewhere in my transparencies, I had that. Yeah, so this is what is shown here is this rainbow. So now let's be more specific. I'm standing here. This is light from the sun coming in. This is the drops in the air. This is actually a very old illustration, and it's not mine. So this is now a specific of scattering. So suppose this is my drop. Then I come here. This is my light. First portion reflects. And as I just claimed, nothing happens. Well, I will see a uniform blue sky. Nothing special. So then I have to go inside, and then of course, next possibility is what we call zeroth order. It comes out. And of course, in all cases, my angle of incidence is alpha. Everything inside is angle beta, and you know with the Snell's law how to relate those. So everything can be computed. Now, this one, it turns out, doesn't give much either. And that happens because, in fact, in order to see this one, you have to look at the sun. So you don't really look at the sun. So therefore, this is also nothing happens. But then the interesting part is the next one is the first order that comes out here. And this is the one you could see. And in fact, it's a beautiful experiment. You can take a glass bottle and do a laser and shine a laser pointer, and you see this light coming out. And then you can vary your impact parameter, and you see at which angle this light comes out. And the scattering angle here is going to be this angle. Then I should mention there is a next one, number 2, which is the same one, and then you can have a third one and so on. So if you look at the picture of this is my impact parameter in terms of the radius of the drop, and this is the scattering angle. So then you see these two lines. So this is the black line is just the reflection, and then of interest are these two lines, first and second. So these are scattering angles, and you see both of those have these flat areas. So it means that the derivative d theta over dB is 0 here. Okay. So and for the other one too. And this is precisely your focusing effect. So derivative, as I was saying, d theta over dB 0 means that this is divergent. So therefore you have a focusing. Now in reality what happens is if you had a drop, if you move your laser, so if you move it that way, so your scattered beam first comes here, and let's say you're moving it this way, then the light first moves that way, then at the critical angle it stops and starts moving backwards. Okay? And because at that exact point you have kind of focusing effect, because there are many beams concentrated in that area, you have a rainbow. Okay, of course the fact that you have a rainbow comes from different index of refraction, but you have a sort of focusing effect where you have an increased cross-section. So therefore you see this here. Now another remarkable part here is along this line only a high order passes through, but in principle so the reflection and first and second order don't give you anything in this area. So there is never an impact parameter that would lead you, or up to a high order, that would lead you to any scattering angle between these two. So And that's actually a dark area. So if you see here, this is the picture of a rainbow from Wikipedia. So you have two rainbows. These corresponds to those two angles. And in between, you have a dark area. And this dark area because no light goes in there. Okay, so this is classical scattering. And I think that sort of discusses everything and gives us an introduction. So the next step is to discuss, of course, quantum scattering. Okay, so in quantum scattering, what we are talking about, or we have to somehow formulate the problem. So in order to discuss the scattering, we have to have some, again, initial state and some final state, so which is very important. So in quantum mechanics, I would have psi initial, and then something happens in the process, and I have psi final. So this is my initial wave function going into final wave function. Now, I do need to formulate it very carefully, because what does it mean having an initial wave function? What kind of wave function that is? So therefore, I always must have some kind of Hamiltonian for free space when nothing happens. Okay. So therefore, I have, we call it H naught, is my initial Hamiltonian, which just a free space Hamiltonian. So this is so these two functions must satisfy that. So I have H psi I equals E I EI psi. Okay, so this is my equation. The same is valid for final. Okay. All right, so I have to have that. Something in between happens. So, of course, Hamiltonian in between can be very complicated. And in principle, I don't need to know the exact evolution between initial and final intermediate times. I only need to know how this initial transfers into final. So therefore, what I need to have is, or I can define, is the time evolution. So I would have U as an evolution operator, which takes me from T naught to T. And what it means, if I take it and act on psi of T naught, then that gives me psi of at some other time T. That is a general evolution operator. Now, if I take psi of minus infinity far back in the time, then I would define that as my psi initial. And then obviously in the same way, psi of plus infinity, I would like to have as my psi final. So therefore, of course, I have psi final equals to my U of to plus infinity from minus infinity psi initial. So this U between minus infinity, from minus infinity to plus infinity, is defined as the S matrix. So it connects my states, initial and final. So this S matrix defines me a probability with which each initial state goes into a final state in some way. So I have some initial here, and then it may go into various final 1, final 2, and so on. So the S matrix square of it, because we have quantum mechanics here, so this is given by the probability that my final one is reached from initial. And this is given as a square of the S matrix, final one, initial squared, magnitude squared. Naturally, if I started with a fixed initial, all probabilities have to add up to 1. So therefore, I have as following sum rule, that if I sum overall finals of this square S final initial squared, then I will get 1. So this explicitly can be written as, of course, have sum over final. So this is sum S final initial times S final initial star. But this can be written as initial final dagger. So I should have written it as, and that is equal to 1. So, and this is the component of the dagger matrix. So therefore, what I have, in more generally, if I start from two different initials, then I have to have 0. So therefore, I have a what's called a unitarity condition, that my S dagger S is a unit matrix. So this is now a matrix. Okay, and of course you have to think about it as just simply a matrix. Now it's easy to think in a discrete space, right? So if I had a discrete finite number of possibilities in the initial state, I would have this similar finite possibilities in the final state space, and then I can just examine what's the probability I start from here, get somewhere else, and so on. So it's relatively straightforward. Now, however, what is important about S matrix is that it has to conserve a certain conserved quantities. So, and what do we know as conserved quantities? So one conserved quantities is, of course, the energy conservation. So if energy is conserved, then it means that the only possibilities that I have is that my E initial equals to E final. So therefore, it is common to write this S matrix through what we call a T matrix, implying this energy conservation. All right, let me write it in the following way. So we will define S matrix between final and initial as a discrete delta function between final and initial. So of course, an obvious case if my initial and final are equal, minus 2 pi I times the T matrix, and here I would add delta of E final minus E initial. So this will enforce my energy conservation if final is not equal to initial. Okay. So then as a next step, and this is the also T between final and initial, of course. So this is so far is just a definition. So instead of S, now I can discuss T. Then what I can do is I can consider a probability with which I have a transition between initial and final. So I have a probability, as I was discussing it here, is just a square. But I will assume that final is not equal to initial. And in that case, my S final initial squared is 2 pi squared, and then I have, of course, square of I is 1, then I have T matrix squared, and then I have a delta function squared. Delta E final minus E initial squared. Okay, so now this is where a trick that is often used here is this delta function between the energies, and we will have to discuss that quite often in the course. So if I have delta function of E final minus E initial, then I can write it as a Fourier integral, which is 1 over 2 pi, I'll write h bar a little bit later, e to the I e final minus e initial over h bar. And then here I'll have times time, t. And here we'll have to write dt. But because there is t over h bar, I need to add h bar here to make it a full differential. So this is the Fourier form of the delta function. So it's just the form of the Fourier integral going from minus infinity to plus infinity. So therefore, I can substitute one of these delta functions with that one, which will lead to a cancellation of 2 pi. So I'll have 2 pi over h bar left. And then I will have T matrix squared, final initial. And then I will have delta function, E final minus E initial, times this integral. Now, but in this integral, because I already have one delta function, so this is clearly 1. So in essence, this is just an integral of dt. And that brings me to another important part, that what I have considered here is the probability, right? So this is p. So if I take this probability and I look at it as some dp over dt, the probability per time, which I called omega before, final initial, then it is just the same expression, but without this integration over dt. So that is 2 pi over h bar, T matrix squared, delta of E final minus E initial. Okay, anybody knows what this expression is called? Fermi golden rule. So this is Fermi golden rule. There are many ways to derive it, this Fermi golden rule, but I think this is sort of an easiest explanation. What happens? Okay, so now the into two deltas, yeah. Yes, because this is forced by the other one. There are many other derivations from stationary formalism, from non-stationary formalism, but I picked this one because I think this is the shortest derivation. Okay, so and this is our starting point for reaction theory, because this gives us the rate which we need. Right. So, and in fact, at the map of nuclei that I showed you earlier, you saw that many nuclei decay. So many nuclei are not stable, and that rate gives you a possibility to calculate their lifetimes, of course. So if you prepared a certain state and your state is decaying, then you will have this rate given by that expression. And now maybe the first step to address is you will have a delta function of energies. So how do we evaluate this, or how do we treat the situations when I have a delta function? So it turns out that, of course, what I need to do is I have to now discuss a practical situation. If I have a detector, and detector measures something, so this detector measures a certain states, and there may be many types of states that have the same energy. For example, naturally, if a particle has a spin, but I never measure a spin, then spin up and spin down are totally different quantum mechanical states, but they appear at the same energy, or they can have the same energy. So this is the situation when this one will work. Now, that was a discrete example with the spin. But if you have a continuous spectrum, then what you're coming to a problem is you need to describe it through the density of states. So your issue is that you need to address how many states at a certain energy you have. So therefore, formally, if we discuss density of states, then what I have is I can define, let me call it nu, as a function of E. So if I have a discrete system, then it's just a sum of all my states I of delta E minus EI. So this is formally a density of states. Now, it's in a discrete space, and you can think of it as if I have a spectrum, then these are the states somehow distributed. So this is state number 1, 2, and so on. And then around each state, I will draw a delta function. If there are many, many states, then this delta function will give me some kind of continuous curve. All right, so that is in the discrete case. Now, if I have a continuum, then I have to, of course, discuss what kind of continuum. And the simplest one to consider is one-body decay. So, which means, suppose I had one particle, it decays into two fragments. Of course, they have to conserve momentum, so if it's stationary, then it has to go that way. Okay, so as we know, this is a two-body problem, and I will be talking more about two-body problems through this course, but I will immediately state the following, that the two-body problem can be reduced to essentially one relative coordinate, which I hope you know this fact. So you can separate the center of mass kinetic part and the relative kinetic part. The center of mass component of the Hamiltonian describes you a center of mass motion, which is not changing. So it's a fully separable part. So therefore, wave function for the center of mass is a separable component, and it's typically a plane wave, which you don't care. So what I'm saying then is this point, which I draw as stationary, can be moving in any direction in a plane wave, and we don't care about that. We can always pick a frame where this is stationary, for example, where the center of mass momentum is 0. So therefore, I will not talk about the center of mass. So therefore, in this two-body decay, we have two fragments, but in reality, there is only one coordinate between them, which is a relative coordinate. And this is a relative with respect to center of mass. That's all we're worried about. So then if I have one coordinate, then this density of states, so this is 2. So in the two-body decay, if you know from statistical mechanics, this integral, sum over all states I delta E minus EI, is changed into an integral d3x d3r over 2 pi h bar cube multiplied by the same delta E minus, let me write small epsilon referring to the particle degree of freedom, right? So this epsilon, if it's non-relativistic, this is just p squared over 2m. Okay? So this is the substitution that you do in statistical mechanics. Okay? I will probably discuss that a little bit more when we have to normalize our states in the continuum. Okay, so then how do I find the density of so this is my nu of E equals to that. Suppose I'm only, well, let me write it in everything, so I have to clear some space here. So my nu of E is therefore d3x is just the volume, which I can take outside. And again, what we are talking about here is free space. So particles in the free space are plane waves. Now, and these plane waves can be normal, we assume some volume which is like an infinite box that keeps our particles. So this is the volume, and then I have here, d3p here should be, I'm sorry. So this is d3x is the coordinate, d3p is my momentum, which we write as p squared d omega dp over 2 pi h bar cube. And then I have a delta function, but this delta function is a delta function of energy. So this is delta of E minus epsilon. Now it's easy to take this integral because P is related to the energy. So I can write it as dP over dE times dE and then get rid of the delta function. So this is volume P squared d omega over 2 pi h bar cube. And then I have here dP over dE. Now this is so far a general expression. In fact, it's valid both for non-relativistic and relativistic. The only question is, what do I put for this dP over dE? So if I have a non-relativistic particle with this energy, then clearly I have dE over, or d epsilon in this case. Let me write it clearly d epsilon here. So this is d epsilon over dP is P over m, which is just the velocity. So therefore my density of states at a certain energy is my volume, and then in here I have inverse, so one momentum cancels, so I have P times the mass over 2 pi h bar cube, and then I have d omega. Have any questions? Yeah, so let me put an integral just to make it nicer. But in reality, I can also evaluate d density of states. So again, this is the same discussion as I started with earlier, that if you have a count rate, right? So I wrote it as d omega because my detector may be covering some only part of the space. So it depends, what do I know? So it's probably better would write to d density of states corresponding to that d omega. Okay, so now, but then if I want the total density of states, then I have to specify what kind of decay is, because this decay may not necessarily be spherically symmetric. But let's say it is spherically symmetric, and if it is spherically symmetric, then integral of d omega just gives me 4 pi, and what I will get is that this density of states as a function of energy is proportional to momentum p. That's the only variable that I have, and momentum p is a square root of energy because I'm talking about non-relativistic particles. Okay, so this is already an important law for one-body decay, that your decay rate has in some way a trivial component, which is a square root of available energy, which is a kinetic energy. So if you have a nuclei, let's say 2 states, that decay in the identical way, so that the T matrix is the same, but one has 4 MeV of energy, or one produces a 4 MeV particle, and the other one produces a 1 MeV particle, then the question is, which one will decay faster? So let me just give you this more specifically on the drawing. So suppose there is one situation, number 1, this decays into this state, and this is 4 MeV. And the situation number 2 is this decays into this, and this distance is 1 MeV. So which one will decay faster? Otherwise, they are identical. So first one will decay faster, right? And it will decay faster because here I have 4, my final particle has 4 MeV of energy, right? So my energy is 4 when I take a square root, so my density of states is square root of E, which gives me 2, right? So, and otherwise everything else is the same. So in this case, I have 1, so it gives me a square root of 1. So therefore, this decay is 2 times faster. Now, it turns out that actually this law is very well followed. So you always have to divide by the phase space scaling factor. So when we go to a discussion of structure, I will always be talking about reduced rates. And the reduced rates are typically the ones, if you want to determine them from experiment, are the ones where you divide by the phase space factor. Now, this phase space factor can be very different for various situations. For example, in electromagnetic decays, depending on the multipolarity of decays, depending on whether they are electric or magnetic, it behaves in the different ways. For example, for dipole, it behaves as energy cube. Now, also, this assumes a particle that is not charged. If the particle is charged, then this phase space scaling has to be modified. And again, we will talk about that. Now, finally, I should mention an interesting fact that for S waves, it has a discontinuity. So it behaves as a square root. So which is very interesting discontinuity because suddenly your decay rate, so if you change your energy and you pass the threshold, so the threshold refers to a point when decay starts being allowed. If you pass the threshold, then it will go as a square root, which leads to some discontinuities. Okay, so the net result here is that when we're discussing rate, the Fermi-Golden rule, and maybe I should write this, in principle we are writing that our probability final initial is equal to 2 pi over h. So this is now final rate that we will see, T matrix squared times the density of states for that particular decay E. Okay.
Your density of states is more or less the same as I defined with small g.
Okay, that's for students then, yes. All right. So next I would have to relate you this, or try to describe you a picture of how do we get to a reaction cross-section from here. So the simplest way to get to reaction cross-section, or just to give you a brief example, is to discuss a particular problem where I guess I can keep this and okay, so we should consider one example. A relatively simple example is to discuss the following. So suppose my Hamiltonian, this should have been H naught, equals to some H naught plus V. So this interaction V is the one that generates the transitions. Then if I take a Schrodinger equation, then in my Schrodinger equation, H psi of t equals I h bar d over dt psi t. So then what I can do is I can go into a so-called interaction representation by defining another psi prime, which is e to the minus I h naught t psi. So this is just a definition, but when I substitute this in here, so what you see here, when I have I h bar and the derivative, and when my derivative acts, actually I need to do this one, right? So when my derivative acts on this function psi, it acts on two parts. This clearly depends on time. So it can act on the exponent, and if it acts on the exponent, it gives me minus I h naught, and of course this is over h bar as well. So then it gives me, then I have a cancellation here. So, and I just have h. So let me write it this way. So I will have I h bar d over dt psi equals to, so first I will have action on, so I'll have h naught, which comes from the derivative of here, of this one, times e to the minus I over h bar and psi prime, plus the situation when the derivative acts on the second one, which is e to the minus I h naught t over h bar. And here I have d over dt I h bar acting on my psi prime only. So this is the derivative part. And then I have other side is h naught plus v, and here I have e to the minus I h naught t over h bar times psi prime. Okay, so what the role of this substitution is clearly as follows, or leads to the following, that this term cancels with this term. And that only happens because I simply extracted defined my h prime with one exponential term, and this extra exponent, when I take the time derivative, cancels one term. So then I have left this equation, and in this equation, this is my h bar here. So this equation, by multiplying it from the left by plus I h bar, I can rewrite as following: my I h bar d over dt psi prime equals to e to the I h naught t over h bar v e to the minus I h naught t over h bar times my wave function psi prime. So, and this resembles my Schrodinger equation that I started with, except now it's an equation for psi prime, and I have a so-called V interaction, which is an interaction Hamiltonian, which is a function of time. Okay, so formally this equation can be solved through what's called the Born series. And I, of course, can write it as my, let me do the following. Let me also apply this to an evolution, because this psi prime can be thought as an evolution operator. It's the same thing, because if I have derivatives on time, and in my evolution operator, my psi equals u t some t naught of t naught, then, and this is psi of t, then of course I can think, instead of this psi prime, when I act the derivatives, I can think of the acting derivatives on just the evolution operator, because everything else is constant. The t naught here is constant. So therefore the same equation, I h bar d over dt u of t t naught equals to v interaction of t times u of t naught is valid for the arbitrary t naught, by the way. Okay, so therefore I can formally solve for my evolution operator, that my t naught. What I will do is I will just divide this equation by IH bar and then integrate that as a function of time. So when I integrate this, I have a constant. Now, naturally, this constant has to be u of t naught plus 1 over I h bar, integral from t naught to my time of interest t, v interaction, u of t, let me call it t prime, t naught, dt prime. So what I just did, I integrated, and you can check, because if I set here time equals to t naught, then this integral is 0, and I get an identity. That's how I find the constant. Okay, so, and now you see, let me try to erase more things here, that this allows me to solve my scattering problem, or to find my S matrix, as an iterative process. So suppose my interaction is weak. So if my interaction, if V is weak or is 0, in fact, what happens if V is 0 with the scattering matrix? What would be the scattering matrix if I didn't have any interaction? What would it be? So if V is 0, what is S final initial? It's a delta function, right? So it's 1 if final is the same as initial, and it's 0 otherwise, because my state is stationary, it's not changing at all. So therefore, this is just delta final initial. Okay, so that means that if my initial and final are the same, then it's just 1. Okay, so therefore, if I would like to know, if I would like to solve this solution iteratively, and I would like to look at t naught being minus infinity and t being plus infinity, then I can write that my S matrix to the first order is, of course, this is a delta between final and initial, plus 1 over I h bar. And then what I have here, instead of this u, I just put 1, because I don't have anything happening. So therefore, this is just integral from minus infinity to plus infinity v interaction times dt. Okay, so, and therefore, my S matrix, now if I would like to look between final and initial state, is delta final and initial, and then here I have plus 1 over I h bar. So, and here I have my integral in the limit between plus and minus infinity. I have my interaction potential, and then I will do a substitution. But now this is an expectation, right? So this was an operator here, u, which is an operator. Now I will evaluate this operator. So S final initial is my psi final u from plus infinity to minus infinity psi initial. So I will evaluate this, and therefore in here what I will have is the energies. So when I evaluate this, this gives me, it acts on the final, so this is energy final, because h naught is an eigen, is the Hamiltonian, and psi final is an eigenstate of it, and here I have energy initial. So I have e to the I e final minus e initial, and then I have t over h bar, and then this is integrated over dt. Okay, so now I got this, and then you recall if v doesn't depend on time originally, as in here, it was a stationary v, and of course in the interaction picture it does depend on time, but it has this exponential dependence on time. So this S matrix element is delta final initial, and then I have here, so do you recall what is the integral of time of this expression? And here I can take my v outside because it doesn't depend on time. So it's a delta function. Right, so therefore this is, I will write I on the top, so it's this, and this is 2 pi h bar delta function. So this gives me 2 pi I h bar over h bar, and then I have v, but this v is taken between final and initial. So this v initial times the delta function of energy. Okay, so now h bar cancels out, and you look that at this order, my T matrix is just the expectation. So my T matrix between final and initial is just my interaction between final and initial. So, of course, you have to remember that this is the lowest order. So what I did is, in here, I took it to the first order. So I did only iterate this expression once. So this is called the first Born approximation. This is a lowest Born approximation. And in which case this T matrix is just the matrix element between of your interaction between initial and final states. Okay, so now let's try to put everything together in the cross section. So if I would like to know the cross section, then there's one more little step. So if I have to, let me just erase something here, so I think I can erase this. Yeah, I think all of this can. Okay, so what I will need to do is the last step is the cross section, and the cross section is my rate omega, and the rate here is 2 pi over h bar, my v interaction, this v between final initial squared, assuming a Born approximation, but you can still keep t. And then times the density of states, and the density of states was, so it was volume divided by 2 pi h bar cube, and then I had p times the mass, and then I had d omega. So this is, let me write it as d probability. Now, we of course always count probability for one particle. Now, if you want to have many particles, then I can just put n here, right? So if I had same thing measured many times, then I just put how many times I do it. Now, of course, in this respect, then if my initial current, J initial, is going to be my number. My current is the density number per volume, and of course now since I have n particles, I would put n particles per volume multiplied by the velocity. And this is my initial velocity. So this is, if you wish, in non-relativistically, then this is, and please don't confuse this V final initial with that V, because they're different things. One is the volume, another one is the interaction. So this is P over M. Again, for simplicity, we're thinking of a one-body scattering. Particle mass isn't changed, it just scatters. Okay, so therefore, my d sigma cross-section is going to be a ratio of those two, and the ratio of those two is, and cancels out, so it's 2 pi over h bar V final initial squared. Then I have here volume squared. Then I have P, and now let me be specific that this is of course P final, M over 2 pi h bar cube, and then I divide this by this ratio, so this is going to give me M squared over P initial. Okay, so one last thing is, what is this V between initial and final states? So in this one is, if I'm looking at the initial and final states as plane waves, and for this particular problem I would have to assume that they're plane waves, then my psi initial, let's say, is just proportional to e to the I P initial as a vector times my R as a vector. So this is my wave function for initial state. Now, the way I'm discussing it here is that my wave function are normalized as discrete functions. So they are normalized that if I take an overlap of two functions in the box, then I would have to get one. So therefore the question is, what should I put as a normalization here? Have to remember, there are two types of normalizations. One is you normalize them by Kronecker delta, which is just 1 when they're the same, 0 when they're not the same, which is often easy to think about. Now, another option to normalize states when you're discussing in the continuum is to normalize them by the Dirac's delta function. Okay, so these two normalizations are related. Now, normalization, when you would like to normalize in the box by 1, is relatively simple, because you can check it. Suppose if I would like to verify normalization in my one-dimensional box, if I have e to the p x multiplied, so this is my psi, and I multiply it by psi dagger, which is, so this is IPX over h bar, of course, but let me, so I multiplied by IPX minus and integrate over dx. So in one dimensions, this is trying to take this integral psi, right? So you see here that if these p's are the same, so this is psi of p and this is psi of p in this case. So if these p are the same, then again, thinking of one dimensions, this is just 1. So I'm integrating 1 over the whole length. Okay, so if I'm integrating 1 over the whole length, that gives me the length. So therefore, I need to normalize here as 1 over the square root of volume. So that will be a correct normalization. Now, if you would like to normalize it by the Dirac's delta function, then you look at this according to our discussion earlier, where I had this delta function, right? And this delta function has 2 pi. So the ratio of normalization is 2 pi over the volume. Okay, so now I guess this was a little digression, but trying to explain you the normalizations. So here I'm normalizing it as a discrete set of states. So therefore my V final initial, I'm going to evaluate it as an integral between them two. So this is 1 over the volume, and then here I will have an integral v of r e to the I p final r minus I p initial r, and these are all vectors d3r. So this is my integration. So and therefore what I would like to emphasize here is that once I put this inside in here, I will get 1 over the volume. So this therefore is proportional 1 over the volume, and the square of it is proportional to the 1 over the volume squared. So this extra volume cancels out. So nothing depends on the volume of the box that I was assuming for this discussion. So I will not write it because I think it's relatively clear what happens. So at the end, therefore, I will always talk about the volume being 1. So it makes a great convenience to think of volume being 1 because I know it cancels. All right, so this is how we get to the reaction cross-section. So now, as a next part we need to discuss is the symmetries and conservation laws for the S matrix. So the next step in this discussion would be to talk about what's called the partial wave expansion. So this S matrix is a matrix. Well, I erased it, but it is a matrix between initial and final state. And as we already addressed, if the energy is conserved, then the energy of initial and final states have to be the same. Okay. Now, there is also a conservation of angular momentum if your problem has a spherical symmetry. So, and this conservation of angular momentum leads to S matrix being diagonal, we call. So it cannot change two different angular momenta. So namely, if you have a S matrix and then you have L and L prime here, then this is 0 if L is not equal to L prime. So you cannot change angular momentum. And therefore, that makes it interesting to discuss the partial wave expansion. All right, so let me now formally talk about this. Yes.
Here you mentioned that if we choose different normalization, like if we use the delta function to normalize, and then over there we are going to have another extra 2 pi, I think 2 pi square.
Yes.
Exactly in front of the differential cross section. So how can we deal with that constant? Because
Which one? Sorry.
I mean, here if we use the volume normalization, the volume cancels out.
Yes.
If we use the delta function to normalize,
No, you have to use consistent normalization. So for the time, I use delta function, which is a delta function, the Dirac's delta function. For this case, I'm using a Kronecker, essentially, delta function. It's the same one as the delta function between, in my definition of the S matrix for the T matrix, I said delta function between initial and final. So that implies that my initial and final are normalized by delta function here. But you can, of course, change from normalization to normalization. Okay, so what I was going to do is I was going to concentrate more on a two-body problem and discuss with you how do we find the cross-section in that particular case. So for the two-body problem, as I said, I have a two-body Hamiltonian, and this two-body Hamiltonian reduces to one relative Hamiltonian. And furthermore, this relative wave function is expressed in the relative variable, and my interaction is spherically symmetric, so I can do a partial wave expansion. So my Hamiltonian, and giving you some brief reminder of quantum mechanics, if I have a Hamiltonian and it is spherically symmetric, then I can write my wave function psi as And this is an exact wave function, so I can write it in terms of some spherical functions, YLM, which depends on angle theta and phi, multiplied by the radial function, which I will write as UL of R over R. Okay. So if I have this form of my, let me just write it as a proportionality here for now. So if I have this, so I can always express a solution to a one-body spherically symmetric problem in terms of this. And then this is separable, so each L is independent, and of course each M is independent, and each UL satisfies the Schrodinger equation for the radial part, so which is minus h bar squared over 2m, u double prime, which refers to a second derivative, plus v of r, u, and then plus h bar squared L times L plus 1 over 2 mr squared, u equals to energy u. So this is my reduced radial Schrodinger equation. So now, also, if I'm looking at the Schrodinger equation, which is a starting time-dependent Schrodinger equation, which I should have mentioned before. So it's I h bar d psi over dt equals h psi. So now this is just a time-dependent Schrodinger equation. Then having this interaction u, I can define, or you probably know from quantum mechanics, that our density in the coordinate space is defined as the modulus of psi of r squared. Now what I also need for my further discussion is current. So how do you define a current for the Schrodinger equation? Does anybody know how to? So this has an expression, let me write the normalization later. So it has psi star del psi minus the opposite one, psi del psi star. And then here I would have to multiply by h bar over im, 2im, because there are two terms. Okay, so this is the current. Now it's easy to show from the Schrodinger equation directly that this has to be a current, because you can take Schrodinger equation for psi and multiply it by a conjugate function, and then subtract the Schrodinger equation for conjugate multiplied by the psi itself. And it has to be time dependent. And then what you will see is you'll see the so-called the continuity equation, that d rho over dt gives you minus divergence del dot j, which is what we need. Okay, in the sake of time, I will skip this derivation, but if you don't know, ask me later. Okay, so this is important. Now, coming back to my radial discussion, which I have to conduct here. So I have to, this is my radial problem. Then I have my scattering problem, and I have to formulate my scattering problem. And the issue on how to formulate the scattering problem is related to having a full asymptotic wave function, because we're only talking about the asymptotic wave function. So my initial wave function in principle is initial beam is a plane wave. So I think of my picture as my point, there is a scattering initial beam comes, it's a plane wave, e to the I k r, and this is of course in the r direction, and then I have some scattered beam. So my initial beam is e to the I k dot r, and this k refers to my initial momentum. So then I have a scattered beam. Well, actually, before we get to a scattered beam, what is the current here? So this is my initial beam. What is J initial? Well, J initial, we have to take the same steps. So when we take the same steps, when I take del psi, I get IK. Right? From the second term, I get also another IK. So I'm going to get, but there's a minus sign. So actually, this is just twice the imaginary part, if you think of it. So I can do the first term and then take the imaginary part of it. So I get here h bar k divided by m. So which is simply my momentum p over m, my velocity initial, right? That's nice. Okay, so this is my normalization of initial. Now, then scattering happens. So I get something else, scattering. So my final scattered is a spherical wave, in a sense. So, and this spherical wave, as written here, has 1 over r dependence, and this is an outgoing spherical wave. So what I can write it as some angular dependence, f of theta, just for simplicity, I'm going to skip phi because of azimuthal symmetry, e to the I k r over r. It is easy to see that this is going to satisfy the Schrodinger equation in free space, and that's what I need. Okay, so I'm going to take this form, and let's now discuss what is the current J scattered corresponding to this form. Okay, so now I have to take, I'm looking far away, and that's a very important key statement, that if I'm looking far away, I have only radial current. So I'm not looking here, I'm looking very far away, somewhere here. So I have only radial direction of the current. So then, if I'm looking at this term, so I have h bar over 2im. So here I have f multiplied by f dagger, so I get f squared always. And then I have here e to the minus ikr over r multiplied by the derivative d over dr. And here I have e to the ikr over r. And of course, this is in the r hat direction. Hat direction, and then minus the same complex conjugated part. Okay, so this is my divergence in the radial direction only, which I'm only interested in. So in this expression, my derivative, of course, can act on 1 over r. And then it can act on the exponent. So if my derivative acts on 1 over r, then I'm going to get 1 over r squared. So I will get component from here. So if I have this derivative acting on this r, then that leads to j being proportional to 1 over r cubed. Now, far away, if I would like to compute my total net current, my surface area of a sphere that covers it is proportional to r squared. So therefore, if I take an integral of r squared, which is an integral of surface area far away, times this 1 over r cubed, then it's going to go to 0 as 1 over r. And this is integral over d omega, obviously. So this is going to 0. Now, which means that asymptotically, I'm not interested in these kind of components. In fact, this is the key statement why I am assuming the scattered wave, is because I'm interested in so-called radiation condition. I am interested only what happens far, far away. That's where my detector is. And this far away, all behavior which is different from 1 over r is of no interest at all. So there's only this behavior that I can have that is of interest to me. Everything else I'm not going to see because it's so far away. So you can think of it as when I do scattering, some messy things happen around. But these messy things don't matter because I'm so far away. And that's where I'm detecting here. Okay. So therefore now completing these steps is simple. So now you see here is that I will get here ik as before, but now in the radial direction. And in addition to that, I'm going to get 1 over r squared. And the complex conjugate just gives me the same thing. So therefore, my j scattered is going to be my f squared divided by r squared times the velocity in the final state, because I will get h bar k again. Okay, so this is my scattered beam. So, and then if I would like to look at my cross section, then my cross section d sigma over d omega, and of course this is j scattered far away, it's in the radial direction, so my count rate, so I will get my count rate, so this is d omega over j initial, and my count rate is r squared d omega, which is a surface area here somewhere far away. So this is my distance r, and this is the surface angle d omega. So this is how many particles I will count multiplied by j scattered. So times j scattered divided by my j initial. So then if you see here, oops, sorry, I think I should not put d sigma, d omega here. So then you'll see here that I will get r squared cancels out, so I will get just magnitude of f squared times d omega, and under assumption that my v final equals to v initial. So this would be an elastic scattering assumption. Okay, so this is important, and that relates me my asymptotic, or how do I find the cross section from the asymptotic form of the wave function. So now in quantum mechanics, my always wave function is a superposition, or it's a complete wave function, so we are only talking about psi far away as being e to the, so I should write it in this way, with tilde, that it's an asymptotic, e to the I k r, and this is the dot product plus some scattering amplitude f of theta times e to the I k r over r, and this is my asymptotic form of the wave function. And if I take my wave function in this form, then my scattering cross section d sigma over d omega is just going to be magnitude of f squared. Okay, so next thing what I need to do is I need to find this scattering cross section, and for that I need an asymptotics of this initial plane wave. So I need to expand them both in the spherically symmetric way, and this is the asymptotic that I'm going to write you now. So e to the I kr. Actually, I have an exact expression. So this is a plane wave. This plane wave is a solution to a free space Schrodinger equation from which we started. So there's no interaction potential. This is a solution. Now, then I can look at this equation, and if V is 0, then what is the solution for that one? Yes, so these are called spherical Bessel functions. Right? So in principle, there is an exact solution. Now, it's a spherically symmetric problem, so this is sum over all L, and then I have 2L plus 1, I to the power of L, PL of cosine of the angle between these two. That's the only geometry that I have. So I don't have a general YLM here, as I wrote here, because I have m equals 0 only situation, because I have just one angle. And then this is the Bessel function JL of KR. Okay, so this is my general expansion. Now, if I take this expansion far away, that's where I need to solve this problem, then far away, this becomes, and I can again, so it becomes 1 over 2 I KR, sum over all L, 2L plus 1, PL, and this refers to a cosine of the angle, and then e to the I KR minus 1 to the power of L, e to the minus I KR. Okay, so this is my expansion far away of the Bessel function. Now, the simplest one, of course, is to check is if you have L equals 0, then we all know that the Bessel function is just sine x over x. And that immediately gives you this expansion for the sine, that this is e to the IKR minus e to the minus IKR. Okay, and then over 2 IK here. Okay, so this is my expansion. So then altogether in the expanded form, if I combine everything, so I would like to now write my scattering wave function in the form, in the radial form only. So I will have this term here. So this is psi, again, far away only. So this is 1 over 2 IKR. And then I have sum 2L plus 1 PL. So PL is, again, emphasizing that's Legendre polynomial of the angle theta, which is between this K and R. So PL, and then I have here e to the IKR minus 1 power of L, e to the minus IKR. So this is just repeated this part, and then I have plus this term, FL. So in order to bring it to the same form, you see I already have 1 over R, which I need, and I have e to the IKR. So I have these two parts. So the only step that I need here is I need to expand my scattering amplitude, which is F. So F is known as a scattering amplitude, depending on the angle theta. And I can always expand it through cosines of the theta. So this is 2L plus 1 PL, which depends on the theta, times FL. So, and that is a definition. And this goes from L equals 0 to infinity. So I can always expand it in terms of Legendre polynomials of the angle theta. So defining these new constants FL. That is a unique expansion, by the way, because these Legendre polynomials are orthogonal and give me a complete set. So therefore, if I take this expansion, then I can write here, so this is my plane wave, which is this term here. And then I have that term. So I will have 1 over r sum over 2l plus 1 pl. And here I have f, let me make some space, fl multiplied by e to the I k r. So, and you see they're very similar, except what I'm missing is 2ik in here. So let me just add 2ik in here, and then I will have to add 2ik in here. So then I can combine these two as one expression. And in this one expression, I will have 1 over 2ik r sum over 2l plus 1 pl. So, and in here I will get 2ik fl plus 1. And this is e to the ikr minus 1 to the power of l e to the minus ikr. Okay, so now this expression has why I'm working to get this expression. I'm working to get this expression to obtain a more symmetric form. So in this form, all my wave function that I'm interested in and that I know how to compute the cross section is expressed in terms of spherical waves. But this spherical wave has a minus sign, this spherical wave has a plus sign. So in a sense, my scattering is now more symmetric because I have a wave that comes in and I have a wave that goes out. So this is my wave, e to the ikr, of course over r, that comes in, because it has negative in the r direction, and this is the wave that goes out. Okay? So therefore, if you now think in terms of scattering amplitude or scattering matrix for a particular L, then this is your initial, this is your final. So therefore, we define S scattering matrix for a particular L as just this term, 1 plus 2i kfl. So now I have a connection, and my connection is between my f, which is what I need for the cross-section, and my scattering S, which I can compute separately by solving the Schrodinger equation. So I don't know, should I finish now? I think this is a good moment to stop. So, all right, so then I'll finish on this one, and then tomorrow we'll resume the story. And if you have any questions, then you can ask me now or later. All right.